Good afternoon, everyone. Now we are back in our afternoon session. So we have Mr. Ghansham with us from Ansys team, who will be taking lecture on innovation through simulation using Ansys low frequency electromagnetics. So we will welcome you, sir.
Yeah,
You
thank
can
you,
start your session.
everyone. Am I audible?
Yes, sir, you're audible.
Okay, thank you.
Uh,
So, I'll just share my screen. Is my screen visible?
Yes, sir.
Okay, thank you. So, good afternoon, everyone. My name is Ghansham Ambekar. In this session, we'll be looking at low-frequency electromagnetics tools from Ansys. So, initially, we'll have a presentation on tool capabilities and just to know what is the scope of the tool overall. And later on, we will look at one example from the tool itself. Okay. If you have any queries, please put them in chat. I'll try to answer them at the end. So in low frequency electromagnetics, we have a few standard challenges. Well, they are not necessarily low frequency challenges, but overall in engineering, we have complex geometries to deal with. So when we are trying to go through traditional methods, forming system equations, overall system equations for those complex geometries is quite difficult thing to do. That also makes it very difficult to predict or to visualize how the system is behaving. And Nowadays, a lot of advancements are happening, especially from the materials side. So to incorporate all those kinds of materials, to take those materials to their limits, all those kinds of simulations are quite complex to deal with. And of course, we have not just the electromagnetics part, but we have all the other physics that would work on that system in a real world, right? So uh, designing such a system, optimizing such a system, that's the main challenge from the electromagnetic side that we face today. So to resolve some of these issues, the primary low frequency tool that Ansys has is called Ansys Maxwell. So it is a electromagnetic simulation tool. It's based on finite element analysis. Uh, and it, like you can see in the top right image there, it's an image of a machine in which the complete motor is being divided into elements, into tetrahedral elements in that particular case, uh, so as to solve the system with as much fidelity as possible. To do such kind of complex meshing, there is a feature in Ansys called automatic adaptive mesh, which will automate and simplify a lot of this workload. We can look at electric and magnetic field parameters like resistances, inductances, capacitances, losses, forces, all the standard parameters that we generally look for. Visualization is, of course, always a very important and a very powerful aspect of simulations because it helps you make things intuitive to work with. Optimization, of course, is quite important whenever you are designing a real-world product. You want it to be the best that can be done with the given constraints that we have, right? So along with that, along with Maxwell, we have a few other tools like Simpler, our rotating machine expert, and PA expert. So we'll have a quick overview of those tools also. And this Maxwell, this electromagnetic solver, it can also be linked with other tools like for power electronics, you can link it with simpler for thermal, for structure analysis of the same motors. Those linking part for multiphysics can also be done. At the end, we will also have a bit better look at what applications are generally, uh, what are the applications generally for such tools there. So in this Maxwell finite element analysis solver, there are 6 main solvers uh, in which they are broadly classified under static, frequency domain, and time domain solvers. Okay, so for example, electrostatic and magnetostatic, those are the static solvers in which electrostatic solver deals with electric field, magnetic solver deals with the field, and there the things don't change, everything stays static. Okay. Similarly, you have eddy current and eddy current solver, which is a frequency domain solver. So plus there is also an AC conduction solver, which is again a frequency domain solver. So AC conduction is in electric field and eddy current solver is in magnetic field. Okay, so these are frequency domain, but they are static in frequency domain. Okay, so that is why they are generally called as quasi-static solvers. And the third category is transient solvers, that is time domain simulations. So herein you have transient electric for electric fields as well as transient magnetic for magnetic fields. So these solvers deal with any applications where time varying phenomena is occurring. Okay. For example, if you're looking at induced voltages, that would be a function of change in flux, right? Change in magnetic flux. So that would normally come under transient solvers. Okay. Uh, so the solvers are not really divided from a mathematics point of view. They are divided from a physics point of view. Okay. Also, along with Maxwell, there are 3 main tools under the ANSYS low frequency uh, portfolio. That is ANSYS Simplorer. Simplorer is used for circuit system level simulations. Okay, so you can create your own circuits, feedback loops. There are uh, blocks available for it, like you can have sources, signal processing blocks, math blocks, uh, switches, tires, thyristors, equations, all of those measurement, all of those kinds of things are available. And they're not just available from an electrical point of view. You can also have, let us say, blocks related to thermal or mechanical uh, parameters. So you can create a complete system there at one place. That's why it's not just a power electronics simulation tool, it's a system level simulation tool. Okay. The next tool is RM Expert. It's for rotating machines. So if anybody is interested in simulating motors, rotating motors, not linear. For those, RM Expert is an analytical tool. So it's not a finite element tool, but it can do quick simulations for your rotating machines, and also helps you in setting up a 2D or a 3D project for FEA analysis in Maxwell. So all the geometry and all the initial setup part of it, our expert can simplify all those aspects. The third tool is for power electronics expert. That is again, it's mostly done for transformers and for inductors, which are used in power electronics. Like the transformers won't be your power transformers, like they won't be huge. There would be your small transformers which are used along with electronic circuits. Okay, high frequency transformers there. So this particular tool has component libraries from a few suppliers. So the core shapes from those suppliers and the standard shapes of wires and bobbins, all the data is available. So for your given waveform or for your given uh, uh, application. It can help you in selecting appropriate core and bobby and wire uh, models from suppliers, right? So it also does an analytical simulation, and for finite element simulation, it will use Maxwell. Okay, so both RM expert and E expert can do analytical simulations of its own, but when it comes to FEA simulations, it will use Maxwell in solvers. Okay. So some of the key technologies that Maxwell offers is uh, it is first of all a completely integrated and platform for all electromagnetic simulation, both high frequency and low frequency. So today morning there was a session for high frequency. So uh, right now we are looking at a low frequency part of it. Then there is adaptive meshing for static and frequency domain solvers, as well as there are a lot of advanced meshing options available to optimize your mesh to your requirements. So there are a lot of advanced meshing technologies also available in it. There are optimization algorithms, standard algorithms, plus you have support to scripting if you want to do some additional algorithms. You have both 2D as well as 3D solvers. Uh, you can get advanced material properties. We'll have a look at it in a little bit more detail in a minute. Then you can do reduced order modeling of a machine. For example, if you want to run a feedback loop on the machine, of course, you can do a completely, for every time step, you can run both finite element and the circuits together, or you can even create reduced order models for quicker simulations, faster simulations. Okay. And we'll also have a look at multiphysics simulations later on. So the tools, the ANSYS LF tools are distributed as follows. So the main tool is Maxwell, which can get such geometries as well as overall setup from RM expert or P expert or Multithread. And you don't have to take it from these three tools. You can also create everything from scratch in Maxwell. Once the FEA simulation is done, you can couple it with Simplera for system simulation. Similarly, you can also connect it with Ansys for thermal simulations and high frequency solvers for any multiphysics simulations there, right? So together, all of these tools will be a part of electronics desktop. And for anything other electronics, if you want to couple Maxwell, then you go to Workbench. So in Workbench, you can connect Maxwell with ANSYS structural, ANSYS mechanical, and CFD. And all of these tools will together share the high performance computing and optimization options. Okay, they will be common for all. So uh, the adaptive meshing that we were discussing. So if you look at the GIF on the right side, you can see the meshing gets very distributed within the volume there. And you can see in the areas where the requirement is critical, more elements are put in. Okay, so this intelligent use of elements or optimum use of elements is what adaptive meshing gives you. Okay. Then these are some of the meshing options that are available. So you can have, for example, a cylindrical gap mesh. That means between, say for motors, between rotor and stator, there is a cylindrical shaped the air gap. So you can mesh it with cylindrical gap treatment in a way that it introduces least amount of error for the given elements used. Right. Similarly, you have for meshed, if you skin mesh can be used for conductors which has skin depth. Similarly, you have flow mesh, which is used for reducing noise during coding or for such kind of simulations. Uh, Apart from meshing, there are also options for optimization. So some of the examples are here. You can do parametrics, you can do sensitivity studies, you can do tuning studies, you can do statistical analysis of your design of experiments. Right? So your set of experiments, you can even do statistical analysis on it. So plus you have a lot of optimization algorithms, about 8 to 10 standard algorithms available, which you can use for multivariable optimization, constrained or unconstrained optimization. So yeah, you will get a lot of options here to optimize your design. Any kind of input parameter, like it can be material properties, it can be dimensions, it can be, let us say, the value of currents or voltages or anything like that. All of these things can be used for optimization. All of these parameters can be used for optimization. Okay. There's also a key technology called high performance computing. So what happens with finite element solvers is sometimes they can get very complex, and uh, they may require a lot of hardware resources. So high performance computing helps you in that. So it can help you with using multi-threading, like you can use multiple cores if you have available in the system. You can do parallel simulations on multiple cores. You can do time domain decomposition, uh, do domain decomposition. Both things can be done. So it will basically help you in speeding up your simulation by using the hardware that you have available. Okay. So uh, apart from that, the transient solvers also give you an access to motion. Okay, so the motion can be both 2D, 3D, uh, sorry, motion can be both linear or rotational. Uh, for examples, on the bottom right column is actuator, which is a linear movement, okay, within a limit. And there can also be a linear machine, which can move indefinitely in the in a linear fashion. Plus you can have rotating machines. You can have multiple rovers rotating simultaneously or multiple linear movements simultaneously, right? So these kinds of motion are available. And there are multiple technologies that help us with that, like there is sliding machine technology for rotation, and there is a spherical rotation motion. For example, in structural walls, you may have uh, rotation which is partial and limited to geometry constraints, space constraints. All those of rotational motions can be done non-symmetrically. Uh, the next thing is material modeling. So you will find a huge amount of freedom available for you to define a material. You can define it in a lot of detail. So you can start with a simple pH curve if you want. For example, for optical states, generally a simple uh, magnetization curve is sufficient. pH curve is sufficient. The linear pH curve, or for transformers, we have anisotropic pH curves. You can have laminated geometries, solid geometries, licks, wires. You can, for permanent magnets, you can do the complete 3D vector hysteresis. Okay, so at every point inside the magnet, it can do the complete hysteresis loop along with the minor loops. So you can get almost realistic kind of performance from that magnet. Okay, both magnetization, demagnetization for all major loop as well as minor loops, right? Uh, you can have temperature dependence of material properties, like your pH laws can be temperature dependent, your pore laws can be temperature dependent. So, and from the magnetic field side, similarly from electrical field sides, you can have nonlinear JE curves, nonlinear DE curves for insulation modeling, for conductivity modeling. So yeah, you will find a lot of options available from material properties side. Now, the system simulation tool that is simpler. So you can see here some of the types of blocks available. So you have in Simplorer, that is, you can have state machine blocks, you can have analog digital blocks, you can have AC blocks, like frequency domain blocks, time domain blocks, as well as static blocks. Okay. So with frequency domain blocks, if your simulation is done in frequency domain, you also have Bode plot, Nyquist plots, polar plots. For time domain, you have rectangular plots, stacked plots that you can plot there. You can also have digital plots or digital blocks also with it. So you will find, along with equation blocks, you can signal processing blocks. You will find you can build a complete system there. So if you look at the example on the right, all the different aspects are being brought in. So, for example, the motor can be brought in from Maxwell. You can bring in, let us say, the transmission shaft from mechanical structural. You can bring in batteries from Fluent. So, multiple ancestors, you can create components, model components, and bring all those modeled components at one place to see how they all work together, right? Uh, This also helps you in figuring out conducted emission. So there are LISN ports also for those. So you will find a lot of options there to work with. Uh, as for uh, the simulation, as for the fidelity levels, you have there are basic blocks also, motor blocks in Simplorer, but other than that, motor is just an example. It doesn't have to be motor. You can have any kind of systems brought into Simplorer, electromagnetic systems. So there are some standard systems, transformers, motor blocks available. Plus, you can have RM expert or P expert blocks brought in, which will be a little bit better. Then you have the most accuracy possible through a coarse simulation with Maxwell. That is, at every single time step, both your circuit as well as your FEA model in Maxwell works simultaneously. So anything that happens in the circuit will affect the FEA simulation and vice versa, right? And the last option is the EC model or the reduced order model, in which we create the reduced order model from an FEA block. But later on, for any longer simulations, we use EC models. For example, if you want to see uh, how is the motor going to behave or the drive going to behave after a while, let us say half an hour, 1 hour. So those long-term simulations you cannot really do with FEA solutions running with the middle option because it takes a lot of time to do. So in those cases, the reduced order model will do it quite quickly. Uh, there are also multiphysics simulations, which you can do with Maxwell as a source. So some of the things that can be a source are like you have torques, you have forces, you have losses, and there are multiple types of losses. You can have core loss, eddy current losses, ohmic losses, right? For electric field solvers also, you can have dielectric losses there. So you can have multiple types of losses that can be calculated. Similarly, you can calculate forces on objects. You can forces on objects as a whole or the force distribution on the object surface or throughout the object volume. You can calculate forces there. When it comes to linking all these Maxwell inputs to the other tools, we do it through uh, we do it through Workbench. So in there we have a, a very simple drag and drop kind of an interface in which in Workbench you bring in Maxwell. We can bring in the other tools like you can see here, this steady-state thermal and structural plotting. And you can share the solutions with each other. You can share variables with each other. You can share materials with each other. So this is the Workbench acts as a interfacing tool for all of these different solvers, multiphysics solvers. A few other simulations like that is you can have model analysis, NVH, fatigue analysis, stress analysis. All of these things can be done with Maxwell, uh, along with with coupling with Maxwell. Okay, here we have one simulation for one example for thermal multiphysics. So in the first case, magnetic field solver calculates the electromagnetic losses, okay, as well as the loss distribution inside the volume of the motor. In this case, it is a motor. It doesn't have to be a motor. Those losses are transferred to a thermal solver where the losses are mapped, like the loss distribution inside the volume is mapped. And from that loss distribution and along with all the thermal uh, environments, the thermal conditions that are there, the fluid conditions that are there, you can calculate what temperature would those losses uh, result into. This temperature distribution inside the volume can again be brought into Maxwell. So your Maxwell molecular properties can be a function of temperature. Both your pH curve and BP curves can be a function of temperature, and you can resimulate with these new uh, temperatures there. So the loop can go over and over, and you can get a good understanding of how the motor is going to behave with your specific thermal environment. So uh, along with that workbench coupling, this is an example where the coupling is happening within electronics desktop itself. So electronics desktop also has a basic thermal solver, has a thermal solver called ISPAC. So you can, so in this case, you can couple Maxwell with ISPAC straight away within the uh, electronics desktop. There is also a mechanical structural solver in electronics desktop. So uh, you can do that too through AD, electronics desktop itself, AADT itself. So one good thing about Workbench is that you can share parameters. So if you are doing optimization studies across multiphysics simulations, you can do those. So you can share the parameters with all the solvers so that when you run any kind of optimization, the since the variables are same throughout, the solvers will work in synchronization, and you can run your optimization more smoothly. Okay. Uh, so there's also a third-party coupling option. So just like we can couple Maxwell with Simpler, you can also couple it with Simulink if you want. You can couple Maxwell directly with Simulink. You can couple it both as with FEA for co-simulation as well as with reduced order model, that is the AC model, right? Uh, there's one additional, just like we have products like Maxwell, Simpler, and RM Expert and P Expert, we also have a product for material database that is Granta. So it has about 500 plus materials for electromagnetic simulations itself. Okay, so uh, they are distributed uh, from suppliers also, like the categorization is from a supplier side also. Like you can have TDK, JFE Steel, various suppliers basically you can have their materials under it. A few applications where Maxwell is generally used is, of course, you have actuators, you have cables, you have switchgear. Okay. Uh, you can also do uh, parasitics, you can do wireless charging kind of simulations. Then for electrical machines, you can do, of course, the motor simulation, the harmonic stress coupling of the motor, the complete vector spaces modeling of the machine, right? The thermal simulations of the machine. For transformers, you can do insulation studies, like how the insulations are behaving, how the electric field stresses are, what are the losses, what are the induced currents inside tanks, inside the structures around the transformer core. Uh, then for wireless power transfer, of course, Maxwell and HFSS both can do in their own envelopes, like what you can see in the top left corner. Some portion of wireless power transfer works well with Maxwell, that is the low frequency side of it. And then some part works well with high frequency solvers. Okay. So depending on what is your operating condition and what is the application, you can decide which solvers to use. On the right hand side, you can see there is a circuit with a Maxwell model in the middle, and both the transmission and the receiving end of the wireless power transfer coils model there in the circuit. Uh, for power electronics, you can have, of course, the loops, control systems like feedback loops. You can have converters, inverters, bus bars if you have, or cables if you have there. All of those things can be simulated. Okay. For cables specifically, the voltage distribution, electric field distribution of the cables, the performance of cables, like their frequency response, uh, you can study that. You can study the voltage distribution within bus bars, the current distribution within bus bars, also the Lorentz forces acting on these cables. You can study all of these different aspects there. Uh, for actuator solenoids, since we can do the complete vector hysteresis, you can deal with issues like remnant fluxes, right? So these advanced advanced solenoid simulations, wherein the residual fluxes and the temperature, all of those things affect your performance, your force of a solenoid. Those kinds of simulations can also be dealt with. So this is just an animation where you can see how the magnetic field is getting diffused within the structure, within the volume of the solenoid. So this diffusion takes a little bit time. So your actuation time of a solenoid is generally a function of this. So you can do these simulations. Since you can do all these electronic simulations, you can also use them to characterize sensors, right? Designing sensors, characterizing sensors. So a few examples are available here, but sensors is, well, there are a lot of variations available in sensor. So electromagnetic type on for sensors, depending on the electric field or magnetic field, you can use Maxwell there. Okay, so uh, to just to sum it up, uh, you for low frequency electromagnetics, for parameters like resistances, inductances, forces, magnetization, all of these things, along with circuit simulations and multiphysics, is what Ansys Maxwell and the other ancestors will offer you. Okay, so before we go to uh, a demonstration of Ansys Maxwell, if you have any queries, we'll just have a look at that, and then we'll go to the demonstration part of our session. So uh, will HFSS and this together give the required simulation? Uh, So HFSS is for high frequency applications. Maxwell is for low frequency applications. So generally speaking, uh, HFSS applications itself are different than Maxwell. But of course, there is some overlap between them. But most of the time, things are quite different. Like, for example, you cannot do a motor simulation in HFSS, and similarly, you cannot do an antenna simulation in Maxwell, right? So generally, they are different from each other for for most of the applications. Uh, will you be able to model robotics model in Maxwell? So yeah, you can do robotics models in Maxwell. Uh, it depends on what you're doing. So robotics is a multiphysics uh, application. So the magnetic field and electric field side of your robotics project can be done in Maxwell. Okay. For anything else like structural or thermal or anything other, rigid body dynamics, whatever it is, all those things will be done with Ansys Mechanical or Ansys CFD. Uh, there's a question, can you import MotorCAD? Yes, you can import MotorCAD. Uh, MotorCAD is also an Ansys tool, especially it is a bit advanced tool than RM Expert, but it comes so it's limited to a 2D simulation, but it's a specialized tool for machines, FEA-based tool for machines. Okay, so uh, many times what we also do is we do the initial simulations in MotorCAD and then we bring them in Maxwell for 3D simulations. But to get an understanding of electromagnetics and thermal and overall uh, envelope efficiency map envelope of the motors, we use MotorCAD. There's a question, is it necessary to have Workbench link while using IcePack AEDT? The IcePack AEDT does not require Workbench link. You can connect Maxwell and IcePack AEDT through uh, electronics desktop itself. Any other query? Uh, it seems there was some issue with the audio. I hope it is resolved. It might be a network issue. So yeah, if there are no more questions, we'll look at the tool itself. Okay. Uh, there is a question from Abhishek Sahu, but I didn't get the question. So if you could clarify that question, I'll attempt to answer it again. So let us look at the tool. I'll share my screen. I hope my screen is visible. So this is this is the Ansys Electronics Desktop AEDT. Okay. So uh, it will it has a few windows you can see open here, like Project Manager. You have properties, Message Manager, progress. So the project manager is it's kind of like a folder in which you can have multiple designs inside. Okay, like you can have maybe a Maxwell 3D, a Maxwell 2D, or a Maxwell Simpler, whatever. You can have multiple designs in a project. Okay, uh, whatever you are selecting, its properties will come in the properties window. Any information in messages, any errors, all of those will come under message manager. And the simulation is generally visible under progress. Okay, so uh, we will have a look at one motor simulation. So there are a few standard examples here. I'll just open one of them to show you. So you have examples for Maxwell, Mechanical, RM Expert, everything. So I'm opening RM Expert, and let's open a Edge synchronous machine. I have kept this simulation solved already in background, just as backup. But we'll try to solve it once more here. So what we have opened is a RM Expert project. So you can see at the top here under projects, you can insert various types of projects. Like you can have high frequency projects, you can have Maxwell, you can have RM Expert Simpler. All of these different types of designs you can insert in the your main project there, project folder. So under once you insert an RMX project, for example, this is for an edges per synchronous machine, or it's just another name for a PMSM, what we generally call PMSM. Okay. Similarly, you have a few other machine types available, like you have brushless permanent DC motors, induction machines, DC machines, claw pole alternator, synchronous motor, LSPM, line stack permanent machines. So you have all the standard kind of machines available here under RM Expert. So RM Expert being an analytical tool is kind of template driven. So whatever options are available, you can work with those. If you have anything other than these, you can straight away go to Maxwell and start your simulation from scratch in Maxwell. Maxwell can, well, it doesn't have a lot of limitations because it's much more generic and much more versatile to use. Okay, so the example that we are looking at today is for just pure synchronous machine. So for this particular machine, you have a stator, you have a rotor. In stator, you have some slot shape available. You have a winding configuration that is defined. Similarly, for rotor, you have a rotor with magnets on the outer surface here. In this case, uh, a magnet material property defined. So this is a XG magnet, but you can have, there are multiple magnet materials available. You have multiple ferrite magnets and DFA magnets, SMCO magnets. So you will have a wide library to use with, even from specific suppliers. So if you are, uh, for example, there are various suppliers like, um, I misclicked, hold on. So, for example, there is Arnold Magnetics, Shinitsu, TDK, JF Steel, and then if you have Granta licenses, then under Granta there are even more supplier libraries available. Okay, but a lot of standard libraries are still available here. So you can also create your own materials. So if you don't want to use any of these, you can create your own. So let me just save as desktop, just to, okay, fine. And once you have your machine parameter like its dimensions, outer inner dimensions, the winding configuration, everything defined, you can run the simulation for a particular output power for some particular voltage at some particular RPM, right? So operating point you can define, simulate the design. RMS, but being an analytical tool, the simulation happens within seconds, so it doesn't take a lot of time. So once the simulation is done, you can look at some of the performances, like you can look at some standard curves of the machine. Also, you have some standard parameters from the machine, like you have the slot fill factor, you have rotor data, permanent magnet data, material consumption, steady state parameters, no load, full load parameters, right? Like efficiency, losses, torque. So you can look at the standard parameters, and if you feel like something is here and there, you want to make any changes, you can just quickly go make a change and resimulate. So uh, within a few simulations, maybe you can arrive at at a design which is close enough or good enough. Okay. So once you have a rough design, the fine tuning happens in Maxwell. Okay. So for that, you can just transfer the designs into Maxwell. So a similar thing happens in MotorCAD. So you can design your initial project in MotorCAD, make sure it is from electrical side, mechanical, thermal, and the efficiency map, everything is fine. And then for even on the simulations, you can convert it into Maxwell and do more analysis in Maxwell. Okay. So uh, this is design right now being converted from RM Expert to Maxwell. So what RM Expert will do for us is it will set up the whole project. So for example, it sets up the geometry, it sets up the material properties. Like you have under copper, you have all the windings. Under M1924G is a steel material. So under that you have stator and rotor. Under vacuum, you have some FE related uh, objects like region and band, as well as you have shaft. So here the shaft is assumed as vacuum, but normally it's not that sensitive. Then you have magnet material. Okay. So along with all of these things, you also have a circuit that is running. So this is a very basic circuit here, just a, a simple, there's no feedback loop as such here. There is just a switching inverter, a very, very basic switching logic, and a motor. Okay. So you can have a full-fledged feedback loops in simpler, but this is just a basic circuit for demonstration right now. Okay. Uh, then along with that, you also have windings defined, like you have phase A winding, B winding, and C winding, right? So all the different windings and coils defined. And once all of these simulations are, all of these parameters, the materials, geometry, uh, the excitations of the machine, all of those things, they are more or less automated from RM Expert. If you want to make any changes to those, you can do it now. And once you're satisfied with all the inputs and all the operating conditions, you can just uh, go to setup, set up a stop time and a time step for the simulation, and run the simulation for that particular stop time and time step. So the simulation may take a few moments. So during that, we'll see a few additional things like let us say this steel material. So let's look at the material properties and how they are defined here. So if I look at this particular steel material, you can see it has a pH curve, magnetization curve there, uh, and there's bulk conductivity. So this permeability can be a simple, that is, so mu r can be a constant, or it can be non-linear. That is, you can have a pH curve, or it can also be anisotropic. That is, you can have three different pH curves or three different permeabilities in three different planes, three different like spatial planes. Uh, Then there's magnetic coercivity, which is generally used for permanent magnets. So the permanent magnet's magnitude of coercivity as well as the magnetization direction uh, is you can define that. Then there is a core loss model to it. So there are a few types of core loss models, like you can have electrical steel, which is used for laminated objects. You can have uh, ferrite models like power ferrites for example, you have those ferrite cores, right, for inductors, transformers, electromagnetic transformers. So those would cover this power ferrite model. And then the BP curve is when your uh, losses are a function of temperature, core losses are a function of temperature. So together, they will help us in modeling the core loss of your machine. Okay. You can also have uh, three different types of object, like materials. Like you can have solid materials, laminated materials, as well as Litz wire. Okay. So you can define three different types of uh, compositions of any material property. Okay. The remaining are generally used when we do multiphysics simulations. Okay. Uh, so you can see here the progress window shows the simulation progress, as well as the message manager shows you if there are any messages or warnings or anything like that. Uh, this particular warning is fine; it doesn't affect anything, so I didn't change it. Uh, and even while the simulation is running, you can have a look at results. Okay, so for example, the first thing here is a torque. So if I double click on torque, you can see the torque waveform versus time in this case. Okay, so you can see all the noise that is happening. A lot of it is due to the switching of the inverter. And, the current waveform due to its switching is reflected into the torque waveform. Okay, so you can look at the current waveform also. The next here is the three-phase current. So you have phase A, phase B here, and then you have phase C. Okay, so this particular machine, it's not a sinusoidal waveform applied to it. It's a switching circuit. So uh, all it, all the waveform is, uh, you can see it is according to the switching circuit with all the harmonics included in it. Okay. Similarly, you have the induced voltages. So this is a phase A voltage, for example, almost sinusoidal, phase B voltage and phase C voltage. Okay, with some switching notches on it. The flux linkage is somewhere in between sine and a trapezoidal waveform. But you can see these two shows you the switching impulses in there. You can look at the DQ components like the DQ inductances. You can look at the DQ flux linkages and the DQ currents. Okay. Apart from these, you can also create your own reports. So for example, I can create a rectangular plot for losses. So I can create a rectangular plot for core loss, let us say. Okay. So from category loss, the quantity loss, if I click new report, this is a core loss of the machine with respect to time. Okay. So if I want the average loss value here, I'll just average of it, or you should ideally take it for one electrical waveform. I don't remember what the frequency is, so I'm taking it from 20 to 40. But normally you should take it for an electrical waveform. So the average value is somewhere around 10.8 watts. Okay, so you can look at the plots. You can have multiple plots overlapping. You can look at specific points on the graph. You can have average values, RMS values, distortion, minimum, a lot of risk characteristic functions available here, right? Uh, of course, export the results as, let us CSV file or image or there are a lot of options available. Okay. Apart from losses, you also have inductances, so self and mutual inductances, for example. Uh, phase AA, that would be self, BA, and CA would be the mutual ones. So I'm selecting the three, and so you can see the self inductance and the two mutual inductances are seen here. Okay, so you can plot those. Uh, you can also see the change in inductance with respect to time. It generally happens due to saturation and any harms that are there in the waveform. Uh, of course, you can take a FFT of this result. For example, uh, for this inductance value, the self-inductance, I want to take an FFT of this. Okay, so I can just create it in a new report and click on results, create an FFT of it. Most of it is in the DC or at 0 hertz, but there are a few, uh, you can see points on higher frequency. X is basically frequency, Y is the magnitude of it. It says FFT time because the original characteristics had the name time. So just the name is copied here. It's not time. Okay. Uh, we can see the simulation is over there. So along with these results, the 2D results, you can also see field plots. So for example, I can go to the field overlays and for this particular geometry, I can, let us say, plot flux density. Okay. So this is the flux density distribution inside the motor. Okay, for the whole circle. So you can see the red portion here represents about 1.65 Tesla. That's the maximum. And blue areas are all zero. So this is the magnitude of flux density. That's why there is no north and south pole. So there's no negative, but yeah. Similarly, you can also look at the flux lines. That is the contours of your magnetic potential. So here you can see uh, the flux lines quite uh, clearly. They are going through the pole and then through the teeth yoke back from teeth to the next pole. Right. So the complete flux loop is visible here. This particular flux loop and the field you can even animate it. Okay, so you can see how it varies with time. So I'll select a few time steps and let's try to animate that. So you can see for those types that we selected, how is the rotor rotating. Okay, so you can, at any time, you can zoom in and observe what is happening at every single time step, right? So that will help you in deciding what needs to be changed and where it needs to be changed. So this doesn't have to be a motor. It can be anything. It can be a transformer, actuator, a capacitor, insulation. It can be anything. So you can observe and study the uh, circuits, the systems like that. Okay. Just like we have flux density and the flux lines, we also have uh, let us say losses. So I can plot the core loss distribution. So at 0th second, it is all 0. But if I change the time step, let us say to 40 millisecond, you can see there is some core loss distribution for 40 millisecond. The scale is not that good. I just change the scale. Let's make it a log scale. Okay, so that's the core loss distribution inside the stator core. For rotor core being synchronous, the core loss is quite low. So yeah, so these are some of the output parameters that you can expect from uh, motor simulation using Maxwell there. Now, apart from these, you can also go into much more details if you want. So, for example, just like you have these result plots, let us say I want the output power of a machine. So output power of a machine is the mechanical output is what torque into speed, right? So just like we have torque, position, speed, all these parameters here, I can use these parameters to create equations. Like I can take take the torque and multiply it with speed, okay, and create a report. So this will be our torque into speed, that is mechanical power from the machine, right? So you can create your own equations from those parameters. Okay, you can uh, as long as the equation is mathematically correct, you can use it. So you have access to all the standard arithmetic operations like addition, subtraction. You also can do trigonometric functions. You can do exponential, average values, uh, maxima, minima. All of those functions can be used in your equations, and you can work with that. So you don't have to limit yourself to the output parameters available. Similarly, you also have uh, options available in the fields side. So let us say I want to calculate, uh, let us say the average flux density in a tooth, in some particular tooth. Okay, so what I can do is I can just create a line on that tooth. Uh, let us say here at the top, I'm creating one line. Uh, okay, okay. That is just an image. Let me calculate it from here to here. It's not going throughout, right? Um, undo. I didn't click correctly. Okay, so let us say this is a line, and I want to calculate the flux, average flux on this line. Okay, so the name of the line is polyline 1 here. So what I can do is to extract any such field related quantities, I can go to a field calculator. Okay, so field calculator is uh, just as the name suggests, it can be used to calculate or to apply various operations on the field and calculate quantities from it. So you have a lot of operations available, like you have some general operations, addition, subtraction, you have scalar operations and vector operations like integral, cross product, divergence, curl, right? So all the standard vector arithmetic, scalar, uh, vector and scalar calculations you can do here. So you can write your own equation as long as the equations are mathematically correct. You can write them. Okay. Uh, you also have quantities with all the fields. So for example, I want average flux density. So I will take the flux density field. And let us say I only want the flux density in the y direction. So for this flux density vector, I'll take its scalar y component and uh, take the geometry of that polyline, which we just created, and integrate our flux density in y direction on that polyline. So you can build your own equations like this. So this can be by on line. Okay, let's say I'm naming it as by online. Okay. So such quantities you can uh, plot. This by online, I can plot just like we had plotted torque and Bayes in current and losses and all those things. So okay. So this is the flux density in there, the average value with respect to time. Okay. So you can have anything like this, any as long as the quantity is mathematically correct, you can use it. Uh, so yeah, any queries? Probably there might be a few queries. Uh, yeah, any questions? There was one earlier question. While understanding the BH curve, is there any CFD involved? So CFD, that is computational fluid dynamics, that is done through Ansys Fluent normally. There are a few solvers, but one of them is Ansys Fluent. Uh, and so for CFD, you will have to go there. Maxwell will do the electromagnetics part of it. Okay, not the CFD. Any other question? There are a few. Does the software suggest changes that might improve the performance of the device? Uh, the general option, well, a simple answer would be no. The software does not suggest anything to us per se. There is no intelligence in it. Like it's, uh, but what it can do is it can help you to determine what needs to be changed. So the decision would be yours, but it can help you in determining what needs to be changed. For example, in our earlier that in this motor project, the tooth flux density inside the tooth was a little bit more, right? In the yolk, it was a little bit more. So looking at that, you can maybe decide, okay, you need to work on those two areas. So maybe the tooth might be wider, or you can do something else. So it's not suggesting, but it was helping you decide what needs to improve. Okay. Uh, Then there's one more question. By selecting the geometry, the new window is opening named Design in Spacetime. While selecting the geometry, the new window is opening named Design in Space Claim. Uh, are you talking about Workbench? I assume you're talking about Workbench, the geometry block inside Workbench. Uh, so the geometry block inside Workbench, you can choose both Design Explorer and Space Claim. The default software that the geometry block opens is Space Claim. And uh, but in Maxwell also you have some basic CAD tools available. So uh, I'll just show you the CAD options in Maxwell quickly since we are on topic. So if you look at and that raw, this was a 2D geometry, so there are 2D options. But in 3D, Maxwell 3D, you will get 3D blocks options also here. Okay, so for 2D, you have here points, lines, and then sheets. Okay, so you will also have solids. Then there are some standard primitive shapes like permanent core, slot core, transformer core, coil, right? So there are some standard shapes also available. Plus, with these primitive shapes, you can use some modular operations like Boolean operations, surface operations, fillet, chamfer to create your own shapes. Okay. Plus, you can connect space claim to it. Okay. So if you want to uh, do the CAD in space claim, you can connect space claim to it. Or if you're using any other CAD tool, you can also import and export from the CAD tool. There are a few standard CAD formats that you can import and export. Okay, almost all the major CAD formats are available here. Okay, so yeah, so that is a brief overview on the CAD from Maxwell. So all the basic CAD you can do in Maxwell. If there is any complex CAD, do it in SpaceCAM and bring it in. Okay, for example, the motor geometry we can do in Maxwell itself, but if you're doing the outer, let's say, body of the motor or some any such complex geometries, we generally do it in SpaceClaim and bring them here. Uh, then there's a question if Maxwell can handle multiphysics data. So yeah, when you're coupling Maxwell with multiphysics solvers is in Workbench, the solutions from those solvers, well, depending on what solver and what you're solving, if those things are compatible, they can be brought into Maxwell. For example, the temperature you can bring in back uh, in Maxwell. Ansys has the ability to do a lot of analysis types and interface. Won't it be costly and difficult? So the difficulty part of it is, well, for costly, there are multiple that things, multiple packages available. So the management can decide what can be purchased. But for difficulty, I would say at the beginning, since a lot of students are not aware with the with solving geometry instead of solving blocks, uh, for a first week or so, there is an adjustment period. But after that, if you're good in the electromagnetics, you can easily do Maxwell. Okay, same goes with any other FEA tool. So if you're good in the theory of the structure, you can do structural well. If you're good in theory of CFD, you can do CFD well. Uh, so just a initial for somebody new, there is a small adjustment period at the beginning, but once it is over, things start getting easier. Plus, we do offer trainings and sessions periodically, so you can uh, connect to us and get your queries resolved. Uh, Maybe not a Maxwell question. Can we simulate Hall sensor for measuring speed of the shaft? Yes, Hall sensor can be simulated. So in fact, in the presentation, one of the sensors in the list, I believe was Hall sensor. Yeah, so on the top right corner here, uh, it might not be visible to you guys. But yeah, in the presentation, one of the example was Hall sensor. So what we do, well, what Hall sensor is basically your, uh, it detects uh, it's a function of the flux that is in the flux and the direction of flux within your uh, cross-sectional surface or cross-sectional volume. Okay, your sensor volume. So it, just like we plotted the flux on a line, you can get the flux inside a volume, and it will give you a good representation of a Hall sensor sensitivity. Uh, Multi-domain like coupling eddy current losses and using them for thermal analysis. So yeah, you can do the eddy current losses. You can calculate eddy current losses, core losses, ohmic losses. All of these losses you can calculate and use them for thermal analysis, and that can definitely be done. Uh, uh, so there's a statement about the interface. So yes, HFS and Maxwell has the same interface. So all the electronics tools are slowly getting they are almost all of them are now under the electronics desktop. Maybe just a few are still out there, but most of them are now part of electronics desktop of the part of the same interface. So it's precisely to help users and make things simple for them. Uh, there's a question if this entire process can be done in MATLAB or are there any dependencies in MATLAB, which is solved by Maxwell. So those two tools are very different. Both are good in their own domain, but they are very different tools. Maxwell and MATLAB are very different tools. The complete point of view is different. So if you see, Maxwell is solving the geometry and the flux distribution inside the geometry, whereas what MATLAB does is it solves blocks and circuits. Okay, so in MATLAB, your motor, it doesn't look at the core geometry and the flux distribution and the where the flux is moving through the geometry. All those things are not in MATLAB. They're two completely different tools. Okay, you can couple Maxwell with MATLAB, but like you can have this aspect of the simulation, the field simulation in Maxwell, and the circuit in MATLAB, or you can even do the circuit in Ansys Explorer. So yeah, they are very different. MATLAB and Maxwell are very different tools. Uh, can we give time varying inputs and time changing properties of materials? Yes, you can do time varying inputs. So if I didn't go in a lot of detail here, but this is an external circuit, right? So this particular external circuit, the switching and all is happening. Uh, it's all time varying. Okay, so just like here we have specified that the type is external, you can also have current and voltage sources here. And those current and voltage sources can be time varying. They can be constant values, they can be equations, they can be data sets, or they can be external circuits like this. So whatever you basically want to do, whatever kind of source, as long as the source has a unique value at every time step, you can use it. And it is a continuous function, you can use it. Okay. So yeah, all time varying inputs and time changing properties can be done. So time changing output properties can be your eddy currents, it can be induced voltages, core losses, it can be setting up of flux uh, in the geometry, it can be all of these things. Any other query? Can we predict the breakdown of dielectric material of transformer by adding impurities? Uh, well, not really. Uh, so the uh, breakdown of an insulation, the breakdown itself is a chemical change. Okay, so The Maxwell solver is the electromagnetic solver. So a chemical change is not something that Maxwell can calculate. Okay, so a breakdown will not be done, but it can tell you the electric field stress in the uh, insulation. It can also tell it. You can also define the insulation conductivity as a function of that electric stress. Okay, so what you can do is if the breakdown is causing an increase in conductivity, then you can put the current conductivity as a function of electric stress. That means after a particular electric stress, the resistance will just drop. Okay, and current will start flowing. So that kind of a thing can be done, but the breakdown as a concept is a chemical process. The chemical process cannot be done in Maxwell. You can like you can look at it in a different way and get the desired quantity out. Okay. Generally, we are when we do an insulation study, we are not really looking at the final breakdown. Generally speaking, we are looking at avoiding breakdown, and for avoiding breakdown, the stress in the insulation, the value of stress in the insulation is generally sufficient because that will tell us how long will the insulation sustain that kind of electric stress. So we can work for work on reducing the stress on the object and avoid a potential breakdown in that manner. Okay. So generally speaking, it's not required for insulation studies. Is PCB analysis possible? Uh, so PCB analysis is is a huge area. So if you are looking at something like a microcontroller and how it is working, like how the signal ones and zeros of it, that part cannot be done so, in Maxwell. Like the microcontroller itself cannot be done in Maxwell, but let us say you have uh, any access on the PCB where the current is flowing, let's say a power electronic board you have, okay, which is passing current to your IGBT switch or a MOSFET, a high value of current or something like that. Then looking at the stress, the current distribution inside that trace, and uh, the losses inside the trace, all of those things can be done in Maxwell. Okay. Uh, then there's also another part of PCB that is the interference and the radiation, radiated electromagnetics, that is done using high frequency tools, not in Maxwell. The thermal analysis of PCBs is generally done in ISPEC. Uh, the life of a PCB, those kinds of studies are done in Ansys share log. So yeah, PCB analysis is a very wide domain. Uh, can it work for a VLSI system? So not meant for a VLSI system, but some aspects of it can work. Okay. There's a question of can you give a demo for VHDL simulation? Sure, I'll give. We have time. I'll give a demo of VHDL. Simpler simulations. Uh, can we use it to analyze battery of electric vehicle, like behavior will change with it? So those aspects are generally chemical changes, and well, the battery modeling itself is normally done in Fluent, and most of it is done in Fluent CFD, and some part of it is done in Simpler. Maxwell is generally not used for that. But yeah, of course, if you have very big batteries and if you have any bus bars within those batteries, then those current distributions there can be done in Maxwell. Any other queries? Okay, fine. So let's look at one simpler simulation. VHDL are just VHDL is a kind of block inside simpler. Just have a look at that. So to insert a design, we can just go to desktop, insert a simpler design. Okay, so the interface changes according to the simpler interface. Here on the right-hand side, we have a component library, which has all the different blocks used in a simpler circuit. So simpler is not a FEA tool. It's a you connect blocks and create circuits here basically. So you have blocks like basic blocks like capacitors, resistors, inductors, sources like voltages, current sources, semiconductors like IGBTs, diodes, then some standard blocks like alternator DC machines, synchronous machines, transformers, single phase, three phase transformers. So along with these electrical blocks, there are also continuous blocks like gain function, memory integration, differentiation, source blocks like constant, randoms, step, math blocks like sigma function, cosine, sine, average, tan, all of these things, right? So signal processing block like equation block, you have minimum, maximum, limit, summation. Yeah. So basically, you can create mathematical circuits there. There are state blocks if you are doing state changes. Measurement blocks like electrical, fluid, mechanical, thermal. So if you remember, I said simpler is a system simulation tool. So it doesn't just do field, electric, electromagnetics. It can also work with other physics, right? So all those kinds of blocks are also available there. Then in the physical domain, you have those blocks generally, like fluid blocks. Mechanical blocks are generally used with electromagnetics, like you can have translational motion, like forces. You can have spring, uh, mass, or rotational, like you can have torque, spring, limit, damping. So uh, these blocks are generally used to, let us say, give load on a solenoid coil or load on a motor or anything like that. There are also thermal solvers, thermal blocks. And the signal characteristics, you have probes like F50 probe, power probe, which will help you in extracting quantities out of your signals. Okay. Then VHDLA AMS is just a it's an IEEE standard language for writing these blocks. So the tool is compatible with VHDL AMS blocks. So if you have any blocks, you can just download and import those blocks also. So a lot of standard blocks are there, but you can bring in your own or you can write your own if you know how to write VHDL AMS. Yeah. So uh, yeah, so it's just a different type of block, but you can have similar blocks in it. So the basic blocks are all SML blocks, like a simpler modular language, and uh, you have VHDL as a second language, and along with that, the full-fledged version of Simpler that is Twin Builder that also supports a few other formats like Modelica uh, blocks. Okay. Apart from these, power systems will have blocks like ABCDQ converters. You have uh, control signal PWM, signal generation, as PWM generation. You have converters, cycloconverters, matrix converters, Vienna. And if you are looking at conducted emissions, then you have LS and ports that you can use for it. Then transmission lines, transformers. So yeah, a lot of standard blocks are available here. So you can write your own. You can create your own uh, circuits basically. Uh, Now I'll start with a basic example. So for example, let us say I'm doing an RLC circuit just to show you the interface. So I can just drag and drop, let us say resistance, inductance, and capacitance. Okay. And let us say I'm putting a sinusoidal source along with it. Sorry. So connections are pretty straightforward. Nothing. This tool is not that difficult to learn. So you just take the cursor, when it becomes a cross, you click and start connecting wires. Okay, and there is ground at the top. You can just add a ground. So uh, you have, let us say this is a voltage source. So you can put, of course, here a value or variable or an expression to your EMF value. You also have some standard waveforms like sine, pulse, triangular, so forth, right? So let us say I'm using a sine wave. Let us say I'm putting an RMS value of 10 volt and of 400 hertz. Uh, and I'm not putting any phasor offset. The second tab here is for AC parameters. The first tab for transient and static parameters. This AC parameter tab is used when you're doing frequency domain simulations. We'll see that in a moment. Okay, so for time domain, this tab will not be used. The third tab is output display tab. So what output display tab here does is you have some standard parameters for each block, like you have the voltage across the block, the current through the block. So there are a few out parameters and a few in parameters. Okay. Plus there is an option for showing pen. So for example, the current through the source, if I show pin for it, uh, you can see there is a pin for this block shows the current value. So if I want to use this current anywhere else in the circuit, I can just connect it. Okay, so you can have such pins for each block. Like similarly for resistance also, there is a display tab for inductance. There is a display tab. Okay, so you can set it up. So you can just like our quantity, even the input quantities like uh, the values of frequency, time period, amplitude, all of those input quantities can also be brought into the block through a pin. Okay. There is a database, SDB, standard database. So if anything is added in the database, then at the end of the simulation, we can see all those quantities and results. Okay. So for example, for this resistance, its voltage and current is added in database. So when we do a simulation, uh, let's say I analyze the transient simulation, then in the output results, you can see the current of the resistance, that is R1 resistance current, and the voltage of resistance, R1 resistance dot V. Okay, both of these quantities are straight away available for me to use in the results. So these same quantities, R1 dot I and R1 dot V, I don't have to just use them as results, I can use them during simulation also. For example, if I had let us say a, let us say a comparator block. Okay. So there are two values coming in, val1 and val2 to the comparator. So one of these values can be R1 dot I, for example. Okay. So what it will do is during simulation, it will see at that particular time step what is the value of current through resistance and use it in the comparator. Okay. So I don't even have to do it with putting it as a pane and then connecting the pane. I don't have to do all that. I can straight away use it as a variable. Not just this, r1.I into 2. I can write equations with those variables. Okay, so you have a lot of freedom available. You don't have to put most of the measurement instruments. You don't have to put small addition and multiplication blocks in the middle. You can just put equations in the next block, and a lot of wiring can be eliminated. If you want a wiring, you can make your own wiring through pins. Okay, so you can have a simpler to create circuits. You can, of course, for example, this Maxwell. I'm just copying the project. So this Maxwell design, I can just link it with the simpler. So I can link a Maxwell component, uh, select the design to click on OK, and this is my Maxwell design, right? So I have the phase A in, phase A out, phase B in, phase B out. So the two terminals of the winding, you can connect them, as well as the two terminals of the motion setup. Okay, so like the output of the motion setup can be ground, and the input of the motion setup can be, let us say, a torque source, right? Uh, so you can even bring Maxwell blocks into this. So and connect your feedback loops uh, and do a real-time simulation between the circuit and FEA simulation, both simultaneously, co-simulation between them. So yeah, so that's the quick overview of Simplora. Of course, there are a lot of very, very advanced things available in it, but I'm just giving you a basic overview of Simplora at this point. Any queries with that? Uh, there is one question. Can the simulated data support the plotting of hysteresis curve? Yes, it can. You can. So hysteresis curve is generally an input quantity, but if you are doing magnetization, demagnetization, like the vector hysteresis, if you are doing, then the hysteresis curve does change during simulation, and you can plot the new hysteresis curve. No problem. At any point, you can plot it. Uh, how different is AWaDH compared to Simpler? I have not used AWaDH, so I can't comment on that. Is the query? Uh, yeah, and any other query? Uh, so yeah, so that is what I actually wanted to cover in today's session. So if you have any other queries, we can work with that. Otherwise, we can, uh, if it is okay, we can also end this uh, session a bit earlier. There's one question. Can we add our own equation into the model solver? Uh, equation into the model solver. So if you know how to code a HDL block, those blocks generally are equation based. So you can write your own blocks. Uh, you can even learn SML, and that is a simpler language. Those blocks, you can also write equations through that. Plus, there is a equation block itself, like under blocks, signal processing blocks, there is a equation block, okay, in which you can have some input quantities and output quantities, and you can write equations which will relate those input and output quantities. So equations can be arithmetic, complex, constants, if-else conditions, exponential, logical, right? So trigonometric. So a lot of options are available to write your own equations relating those input and output blocks quantities. Okay, so yeah, you can write your own equations. I don't know in what format you want to write it. Uh, there's no assignment today, uh, but yeah. So yeah, if there are no more questions, we can end the session here. Uh, any questions? We'll wait for a couple of minutes just to see that, and yeah. Uh, how can you download this software? So generally, once an institute purchases the tool, we help in installation and everything for the institute. So you can access it from there. Uh, can I share these files for reference? So I really have to, because these are all inbuilt examples. ASSM1 is an inbuilt example, like I had opened it from example object. So under RM expert, there is ASSM1. So you can just access it from there. So you don't have to wait for me to share that. It's available in the tool itself. Uh, so yeah, any other queries? So there's no assignment from me today. Okay. So yeah, okay then. Since there are no more questions, let's end the session here. Thank you for your time and your patience, and yeah,
Thank you,
thank you.
Mr. Ghanshyam. Thank you for this wonderful presentation. And I'm sure that, so I didn't get that. I'm Dr. Dheeraj Mahajan, actually. So I want to know that the assignments you will be sending to me later on.
No, I'm not giving assignment. I think HF also might not have given an assignment because there is no student version for EM and LF. So for mechanical, there is a student version, so they might have given an assignment to you guys.
Okay.
For LF, there is no student version, so that's why we're not giving an assignment right now.
Okay. Okay. Fine. So this is like a teamwork that they will be doing during the project. I think right now they don't have any assignment. Okay. Fine. I got it.
Yeah. So if the institute has the tool and if students has any query, they can you can through you they can contact us and I'll try to answer them.
Okay, so it is not there in the student version of Ansys. This is what you want to mention. Am I right?
Yes, Ansys has academic versions, but like in mechanical you have a free student version, right?
Okay,
It's
okay,
not there right now in LF.
okay, 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 fine.
Yeah,
Wonderful.
there's
No
no
problem.
free student version right now in LF.
Okay, okay, fine. Thank you, thank you.
Yeah, thank you, sir.
Okay, bye.
Thank you, everyone. Bye.
Yeah, thank you. Bye. Okay. So students, I think we are now breaking out again for I think there's no session again after this. We wanted you to practice the ANSYS part. So you can go ahead and work on it. So for electrical guys, I think assignments will start coming, start pouring from MATLAB from tomorrow's session. So please be prepared. I have already mentioned in that thing, like in the daily schedule, I have mentioned what things you have to do for tomorrow's session in MATLAB. So the electrical guys can start working with it. So we will also share that which student should work on which course module from the MATLAB, that I can also share it today. The dossier is being prepared for MATLAB, how to install and everything. So these details will also be shared by, say, before 6 o'clock today. And yeah, so you are free for today, and the mechanical guys can start working on the ANSYS part. The chemical guys can also start working on the CFD part, and others also, so as discussed. So any question you can ask here, please. Yeah. Gunda Venkata Sai, this is what we imagine. Earlier we were thinking, we were trying to put everyone to do the assignment, but I think it's too impractical right now. So students will be doing, mechanical guys will be doing both mechanical and CFD, then chemical will be doing CFD, metallurgy will also be doing both the assignment, what we expect. Yeah. Mechanical have to do MATLAB. MATLAB is a very, very important tool for mechanicals. Yeah, DFMA assignment will be given tomorrow. This is DFMA. I'm planning to give it to all because of the kind of a generic engineering discussions that we had, so that they should also have a sense of cost optimization and all. So I believe they can also do it. The CSIT guys based on DFMA. It's a fun tool to work on. It really gives you a flavor of engineering. So chemical should do CFD. I'm making a table. Don't ask questions here. I'm making a table that will be shared on the web page, like which branch student has to do which kind of assignment. That will be shared by 6 o'clock. For the time being, you can start looking at the MATLAB link I have given. You have to do one of the course tomorrow in the exercise session. Yeah, Himanshu, I see that it is a course. It's not a course actually. It is part of that assignment. So if you get used to it, it's going to help you a lot. So it is nicely done. So within that course, this is the first question that they have asked. So it is like it's 30-minute session for each session you have to work. I think it's a good exercise to work on. Yeah, mechanical guys have to do, because mechanical guys, there's a lot of competition in mechanical guys. We have maximum application for mechanical, so you guys have to fight hard. On the web page, MATLAB link is shared on the web page um, the daily schedule for the first week. I've shared that thing in the link. I'm sharing it here also. Go to the web page, please. Yeah, MATLAB Academy MathWorks is given. So you will be yeah, so this is our weekly schedule for first week. You can check it there. Abhi Sharma, if you are from mechanical, you have to do both. Yeah, Akshata Patil, the dossier will be shared within say 1 hour maximum. I'm preparing it. I have received it today from MATLAB. I'm just putting the details here. So you will get it in 1 hour. Don't worry. And just a minute. Let me catch up with the other questions. Yeah, Rahul, I'll be submitting things. You'll be getting emails with all details respect to assignment submission and who has to do which assignment, which branch. Just wait for my email. Submit on-site code completion. Yeah, you will come to know, Himanshu, how to submit your assignments. Yeah, electrical student don't have any assignment as of now. Yeah, Shanmukha, Teja, that's true. Mechanical guys are supermans, so they have to do a lot of things. Yeah, right now the assignment related doubts you have to resolve on your own. But in case you have any query, you can send us in the query form. We can get back to Ansys to resolve it. If there is something related to the assignment very strong that cannot be resolved without their intervention. Can we leave? Yeah, yeah, sure. You can leave, please. Yeah, there is no doubt. You can leave, please. Yeah, mechanical is the highest actually. We have a lot of mechanical students. So the competition is high for mechanical. Man, wait, please. These things, the format, everything will be shared. Just wait. Start doing the assignment report submission will take time. I think we are going to open report submission on Saturday only, not before that. So don't worry about submission. Start focusing on doing things. Yeah, aerospace is mechanical. Yeah. Yeah, production engineering will be mechanical, sure. Yeah, I'll not tell this Akanksha. I can't, don't worry about those things. Actually, I really don't know, but mechanical guys, the competition is high, so you have to do work, you have to go through. We'll see how it goes. Sushmit Kumar Sahu, you didn't get query form. Haven't you got an email with the query form before the deadline? Okay, guys, I really need to stop. I have another meeting now. So I think we can close the session. You can work on it. Actually, I'm not able to hear what sir is saying. Can someone please tell? Okay. Don't worry.